Alright, let's talk about thermodynamics. Thermodynamics is the study of energy and energy transformations, and chemists are interested in it because almost all reactions deal with some sort of energy change, energy being given off or energy being absorbed. Let's remember that the total energy in a system is constant, right? And we call this conservation of energy. Right? Now, I'd like to add in, it can always be accounted for, because often we talk about energy's lost here, energy's lost there, and that can be confusing when we are also told that the energy in a system is constant. So I like to always say that it's being accounted for, it's not disappearing, it's not being created or destroyed. So heat is given the letter Q, it's energy, it's measured therefore in joules. It's the transfer of kinetic energy, usually through the particles of the object, and heat is transferred, remember, not cold. There's no such thing as cold, there's only a lack of heat. Temperature is a measure of the average kinetic energy of the particles that make up that substance. We can measure it in three ways. We can measure it in Celsius, Kelvin, or Fahrenheit. We're not really going to use this very much. A couple of formulas. The temperature in Kelvin is 273.15. Oh, there's a bell. 273.15 plus the temperature in Celsius, and temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. If you need to go back and forth, there's some formulas. And the other thing we should realize is that Kelvin starts at 0 and goes up. Celsius starts at minus 273.15 and goes up, but 1 degree Celsius is always equal to 1 Kelvin. The steps are the same, where they start is different. Can I measure the total kinetic energy of an object, your textbook, or the device you're watching this video on? Nope. Too many particles to deal with. Right? So usually we only deal with changes in energy. Yes? Now, if we could find the total energy of a substance, we would be finding the enthalpy. And we go, it's given the symbol delta H, but we're going to be dealing with changes in this amount, so we're dealing with, we're dealing with delta H. No delta up here. Enthalpy is just H. If heat is being released during a reaction, we say that the energy change would be less than 0, and we say that is exothermic. And if energy is being absorbed, we say the energy change is greater than 0, and you use that word endothermic, which I'm guessing many of you've seen those two terms before. Heat is exiting the reaction, heat is going into the reaction. There's a lot of delta H's. We usually smack on these little subscripts like reaction or combustion or fusion, which is melting, or condensation. Don't be thrown off by these little subscripts. This little thing is a naught, it's red, so that's delta H naught. It's telling you the conditions of the reaction, because gases can be a problem. They're very finicky when it comes to temperature and pressure, so all we're doing here is specifying the temperature and pressure of the reaction. STP, circle means STP, 25 Celsius, 100 kilopascals. And now finally, how do we write delta H values into reaction? Here I've got hydrogen and oxygen combining to form water. Energy is being given off here, so it's being made, it's being produced, so it's going to be on this side of the reaction, so I would put plus 285.8 kilojoules. The other way to do this is, instead of actually writing it as part of the equation here, instead we come over here and we write delta H off to the side, kind of rewrite minus 285.8 kilojoules. Because heat is being given off, it's got a minus sign. If heat was being absorbed, I would put a plus sign and I would have this number over on the left side of the arrow. So there's two ways to write this energy value into reaction. Sometimes you want to write them this way, sometimes you want to write them this way, and later on we'll talk about both. One way is good and the other way is better. And that's our short introduction to thermodynamics.